Good afternoon, everyone. Thank you for attending my talk. So today I will talk to you about the analysis of large seismicity catalogs, and in particular I will be talking about the Californian seismicity catalogs. So first, to motivate you, what is our goal? Our goal is pretty simple, to improve earthquake forecasts. So in this goal, one of the main challenges is the amount of data which accumulates at an increasing rate, because we have ever improving and improving network coverage and also improving detection capabilities. So in order to tackle this challenge, we need, in order to be able to extract information from this large data set, we need to develop data-driven objective methods. So in this thesis, that's what we try to do. We try to develop data-driven methods for extraction of knowledge. So in order to give you a brief outline of the talk, first, in the introduction part, I will give you a brief introduction of what are earthquake forecasts and how we play this game and what are the rules of the game. And in the second part, I will talk about one of the main components of earthquake forecasts, which is the magnitude frequency distribution. And then we will also investigate the spatial variability of the magnitude frequency distribution. So in the second part, we will then look at another component of the forecast methods, which is the spatial distribution of seismicity, and for this purpose we will make a spatial analysis of large seismicity catalogs. So in the last part, we will look at a novel pattern recognition method for fault network reconstruction, which will help again in extracting spatial features in our data sets. So to start now with the introduction, what is an earthquake forecast? An earthquake forecast, you can think in terms of a roulette game, where you go and you bet, but instead of betting on numbers, what you bet is you bet on grid cells. So you grid whole California into grid, and you place your bets trying to predict how many earthquakes will happen in each grid cell. So the rules of the game are simple. We have long-term bets only for 5 years, and we consider only magnitudes above 4.95. And also, again, we have a spatial gridding. So we have 1/10 of a degree gridding, and we are trying to play this game within this grid. So the state-of-the-art strategies in this game are, if you didn't know anything, like as if you were in a casino, you would put your chips randomly, uniformly. But because we know better than this in the earthquake business, what we know about earthquakes is that the magnitude frequency distributions follows the Gutenberg Richter law. And next, we know that the locations are not uniformly distributed in space, that they cluster in space. So we can use these two informations to our advantage and to try to forecast earthquakes better than a uniform, no prior knowledge case. So first, we will now look into the Gutenberg Richter distribution. So we will look how this distribution, if it at all varies in space or not. So if we want to know the probability of any magnitude, the Gutenberg Richter law that you see here expressed as the cumulative number of earthquakes for above any given magnitude is expressed by this probability function. And here this is the Gutenberg Richter law p-value, which governs this probability. So if we want to see if there's a spatial variation of this value, what we can do is we can randomly make segmentations of our regions. And within this region, we can write for all the earthquakes within each segment, we can write the joint probability like this. And then by summing up, by calculating the overall joint probability in all these individual regions, we can write the total likelihood of this model. However, because different tessellations can have different numbers of regions and correspondingly different number of b-values, we also need to penalize this complexity. And for this purpose, we use the Bayesian information criteria, which gives us optimal trade-off between a complexity of a model and the fit of a model. So when we do this thing, we can then rank any random tessellation, and here I show you the top 3 solutions of such a ranking. We can rank them. And then what we can do is we can ensemble the top ranking models and create an ensemble b-value map. So here what you see is the ensemble b-value map for California, given this catalog. And what you immediately see in this map is that we have 2 distinctive regions. One of them is the southern California, and one of them is the northern California. And what we see here is that the North California seems to have a larger b-value compared to the south. But what we can prove and what we can demonstrate is that this discrepancy is mostly due to the network inconsistencies And by inconsistencies, we mean the way they calculate magnitudes. Another feature that you would see here is that here in the offshore Mendocino region, we have a significantly low B value. And we were also able to demonstrate that here, because it's an offshore region, this feature is driven mainly by magnitude errors. So the last feature that you see here is the geysers region, and the abnormally high B value here, we see that it's caused by non-tectonic features due to the geothermal activity in this region. So having made these observations that we have significant variations of B value, we are now asking the questions, can we use this information to improve our earthquake forecast? And for this purpose, we will try now to create an earthquake forecast. And for this purpose, here I show you this, again, the Mendocino region, and here is the Voronoi cell for this particular model. And the B value at this Voronoi cell was estimated to be 0.87. And if we now want to distribute the probability of earthquakes within this region, we have to have also a spatial model. For spatial modeling, we have two different approaches. One of them is the relative intensity approach, which basically consists of counting the number of events in each of those 1/10 degree cells, and then distributing the probabilities accordingly. The other one is the variable kernel approach, which basically provides you an optimal isotropic smoothing of these rates, so that you would get a smoothed out probability density in space. So when we apply these two methods, what you would see here in the whole Californian forecast is that the relative intensity method gives you more concentrated rates, earthquake rates, compared to the variable kernel method. Another distinctive feature of this method is also that in cells where there is no past earthquakes, because you are just counting the rates to make this relative intensity, you cannot predict any earthquakes for the future. So when we apply these two methods with our variable B value map, we compare them then with the best forecasting model of this forecast test. We see that 80% of our models, of the best ranking models, outperform the best model. So this gives us confidence that indeed accounting for the B value variation improves forecasts. So having done this improvement, we then go back and we try to look at the second component. So our second component is the space clustering of earthquakes. So in order to investigate the space clustering of earthquakes, we first need to select a catalog. So let's see. So from our previous section, we saw that when we look at the whole California, we have network-related discrepancies because California is so large. So here, in order to avoid getting into these discrepancies of earthquake location and magnitude calculations, we choose to deal only with the Southern Californian network because it's a much vast area. So this leaves us with the Huxen et al. 2012 catalog, which has a total of 500,000 events. So in order to analyze the spatial distribution of these events, you can see that this number is pretty large. So we wanted, thus, to reduce the number of these earthquakes such that we can analyze them in a computationally efficient way. So for this purpose, we exploit the fact that all these earthquakes are not located with the same location quality. So in essence, they have different location uncertainties. So in order to show you a demonstration of how this thing works, how we exploit this feature is, we introduce the condensation of seismic catalogs approach. So here, to give you an idealized diagram, here we have 3 earthquakes in 1D, and the quality of each earthquake is represented by its variance, and we rank them according to their variances. So the worst located one is C, and then it's E, and the best one is A. So what we can show is that if we calculate the likelihood that is better explained by better located events, given the worst located locations, we can see that we can transfer this much weight, mass, probability mass, of the worst located one because it's overlapped by a better located one. So this gives us the possibility to indeed explain the probability mass of poorly located events with better located events. But also you see here that in regions where we do not have better located events, the poorly located events are still remain present because indeed they carry information for these regions. So when we apply this condensation technique to the whole Californian catalog, here you see with green, we show where mass is taken away, where its mass is depleted, and in red we show where mass is increased. And what you would see that we have these linear features. So when we overlap on top of this, the fault trace map of California, you can see that these features coincide very nicely with the fault traces that we observe on the surface. So this implies that seismicity which happens off faults is not off faults due to a physically active diffusion process, but it's off faults because of the poor location capabilities of the network. And you should also consider that this network contains events starting from 80s, so it's quite obvious that events in the 80s would have poorer locations than now. So another advantage that we get is that by doing this condensation, we are able to reduce the catalog length by more or less 25%. So when we now once that we have reduced this, the length of this catalog, we can now continue with our spatial analysis. So for spatial analysis, we will use the multifractal spectra analysis. And for this purpose, I should first introduce you to the multifractal formalism. And so what do we mean by multifractal analysis? So first of all, what's a multifractal distribution? So for example, if you take the case of this self-similar aggregate, what you can do is if you put some circles at any given point of this aggregate, and if you calculate the mass which lays inside these circles, if you gradually start increasing the radius of your circles, you will see that the mass scales as r to the power of alpha, as radius with an exponent of alpha. So if this exponent alpha changes from place to place in your distribution, that means that you are dealing with a multifractal. However, if when you place your circles at any place, you get the same alpha exponent, this means that you have a monofractal. What we can also have is that this scaling exponent changes also with radius. In that case, you would have a multi-range, a multi-scale behavior of the distribution. So when we apply this multifractal analysis to our catalog, what we see is here, you can think of in terms of the q-axis here represents the density, the density of the regions. So as q is increased, you are getting more focused on more dense regions, and when q is low, you are focused on more sparse regions. And the color here represents the clustering strength of these regions. And what we can immediately see is that for California, we have two distinctive scaling breaks. So as you can see here at 2.2 and at around 15 kilometers. So what we then ask ourselves is that what could be the possible origin of such scaling breaks? So the possible origins can be physical constraints, and we know that because we have a limited seismogenic thickness in California, if you are within this seismogenic thickness, which is about 30 kilometers, then you would be in an embedding dimension of 3. However, when your radius exceeds this dimension, exceeds this range, you would be starting to see the dimensions as if you are in a two-dimensional space. Imagine that you have large spheres here. So we can explain this large-scale transition with the physical constraint of the seismogenic zone, with the thickness of the seismogenic zone. However, for the small scale, what could happen is that we can observe such a scaling break due to, for example, location uncertainties. However, we know that in this catalog, the location uncertainty is quite better than 2.2 kilometers. So what we are left with the suspicion that this small scaling break could be the result of the artifacts due to the parameter choices used in the relocation of this catalog. So in order to get rid of our suspicion, we decided to relocate the catalog with an absolute probabilistic method. So as you might already know, any catalog relocation requires that you must have a good velocity model. So for this purpose, we used the VELEST approach to invert for a minimum 1D model in South California. So what we do with VELEST is basically we take the earthquakes which are constrained by the most number of observations, and then we try to invert for the velocity value in each of these 1D layers, and also the station corrections, which account for the fact that in reality, Earth is not a simple 1D structure, it has 3D features. So these are accounted in the station corrections. So when we make our inversion, we obtain this minimum 1D model, and you can see here that we have a gradual increase of velocity from more or less 5 kilometers down to 7 kilometers at the depth of 30 kilometers. And when we look at the station corrections, which are plotted here, we can see that the station corrections with negative values, shown here in red, correspond very nicely with hard rock soils, hard rock sites, and station corrections with positive values, which are here shown with green, coincide very nicely with soft soil sites. And this gives us confidence that the minimum 1D model that we obtain is not just a mathematical minimum, that it actually has physical relevance for Southern California. So using this velocity model, then we can continue to relocate the seismicity with a probabilistic nonlinear method called Nonlinloc. So the difference between probabilistic nonlinear relocation techniques and the classical methods is that in linearized location procedures, you get an idealized ellipsoid uncertainty for your events because you are linearizing a nonlinear system. However, in Nonlinloc, you are able to take into account not only the observational errors, but also the velocity model errors, and then you are able to obtain much more complete distributions of these uncertainties. So when we apply this method with our new velocity model to the whole Californian seismicity, to Southern Californian seismicity, we obtain our new catalog shown here. And you can immediately see that by comparing these two catalogs, in the periphery of the network, we have a much more diffuse picture. And that is expected because if you are outside of the network, your location quality is decreased. So using this catalog, then we can apply the same multifractal analysis, and we can see if we still see the scaling breaks. And indeed, when we look at our new catalog, we can see that indeed this scaling break is gone. So this gives us confidence that the catalog that we obtained is much more consistent with what we would expect from seismicity. And also another main feature that you see is if you compare the mid-ranges here, you see a significantly less clustered seismicity when you relocate the catalog with a nonlinear technique compared to here, and you can see it from the light colors that the clustering here is much higher. So next, having obtained now a uniformly consistent catalog for California, we continue our search to improve the forecast models by introducing a new pattern recognition technique which aims at extracting spatial features from the seismicity catalog. So in order to give you an overview of how this method works, here we will consider this synthetic data set. And this synthetic data set we created by randomly putting faults with different dips and strikes, and we embed them in a uniform background. So in reality, in seismicity, because we know that earthquakes always occur on faults, what we mean by uniform background in reality is seismicity which occurs on undersampled faults. So if I now color these faults, color code them so that you can see which are the generating faults, you can see that we have several faults here. So our approach to try to extract these features back is essentially a bottom-up approach which starts from the most complex structure that you can possibly fit to this data set and then tries to gradually reduce the complexity of the structure. So what is the most complex structure that you can fit to this data set? Here we have around 200 of small Gaussian kernels. We represent each small fault segment with a Gaussian kernel. And here you see these Gaussian kernels. So then we ask ourselves, if we can, for these Gaussian kernels, we can calculate the likelihood, and we can also calculate the Bayesian information criteria, which penalizes the likelihood for the number of free parameters. So if for this complex network, our DIC is here, around 14 and a half, we ask ourselves, can we then merge individual small features to improve this BIC? And indeed, if we consider all possible merges between the pairs, and we calculate the gain by comparing the merged and the unmerged configuration, we see that if we continue merging these structures by always merging the one with the best gain, we essentially can come down to the optimal case where the BIC then starts going up. So this is the case where the model tells us there is no possible merger here, it can only go bad. So this gives us the optimal reconstructed structure of this data set. And you can see that we have a pretty good correspondence between the features. You can also see that in faults which are undersampled, because all of these faults have random densities on them, we are also, for example, here we have smaller features when they are undersampled. So when we apply this technique to the whole 500,000 events in California, we obtain this reconstructed fault map. And you can see here immediately that you can see features like Landers and Hector mine, and you can see several strands of the San Andreas fault. What you would also immediately see is that in the periphery of the network, we have clusters, Gaussians, which are highly anisotropic and which basically reflect the location capabilities of the network here. So in order to validate that what we did here increases our ability for forecast, we put this reconstructed fault network through a retrospective forecast test. And the way that we did this is that because our catalog consists of events between 81 and 2011, we use all the events which occurred after that, so which are not included in our catalog, which are not included in our fault network. We use all the events with magnitude 3s, and we are trying to forecast their locations with our fault network. So we basically calculate what probability does our fault network give for these locations, for these earthquakes that we did not know that happened. So as a reference model, as a benchmark model to compare ourselves with, we are using the triple S. Triple S means simple smooth seismicity model of Zecker and Jordan. And this model basically consists of isotropically smoothing the past seismicity. So because in this model you have to tune the smoothing bandwidth, and we want to give this model as much power as possible when he's competing against us, we said that we scanned all different bandwidths for smoothing, and then we compared our model with this, all these bandwidths. So what you see in this graph on the y-axis is the negative log likelihood per event. So when this is low, it means that you are forecasting better. And this is the dashed line here is the case of a uniform density. So if you didn't know any better and you say it can happen anywhere, this is the likelihood that you would get per event. And when you optimize with respect to the target events, the triple S model, the best that you can get is here. And our fault network, which indeed was not optimized on these targets, performs much better at the rate down here. Now, what you would immediately probably ask is, okay, you perform better than this model, but what is the use, the societal use for this? Like, how good is this for practical applications? So to give you a brief idea of this, we can then create the perfect forecast. And what would be the perfect forecast? The perfect forecast would be if we put a Gaussian on the location of each of these target events, which happened in these 4 years of period. That would be the perfect forecast. However, you should have a bandwidth for these Gaussians. And what would limit your bandwidth? It would be the location uncertainty, because if you can locate an event only with the uncertainty of 1 kilometer, you wouldn't go and try to predict it with a 500 meters precision. So then we can create this forecast varying with the location uncertainty that we think we might have in the network. And you can see here, if we take a relatively realistic uncertainty of 2 kilometers, we can see that our forecast is still a few orders of magnitude away from this. However, we think that by investigating the temporal relationships between these fault segments, we can indeed improve in the future this forecast even better. So this leads me to my conclusions now that we have validated our fault network. So to summarize what we did in this thesis, first we investigated the magnitude frequency distribution of earthquakes, and we concluded that indeed there are significant p-value variations. However, most of these can be explained by magnitude errors and network inconsistencies. Second, we created a new uniformly consistent seismic catalog for Southern California. And then we showed that by optimally encoding this catalog, taking into account the location uncertainties, we are able to reduce the catalog length significantly. And also we are able to encode this location uncertainty as a scalar weight, which would allow us to conduct spatial analysis in a more computationally efficient way. And the fourth thing that we achieved, that we created a fault network reconstruction method, which gives us an optimally anisotropic smoothing of the previous seismicity, which gives us better forecasts. So in terms of outlook, the way that we can use this result is, for example, we can use this new fault network to model seismicity, for example, in the epidemic type aftershock sequence modeling without a predefined spatial decay. We can use now our optimally anisotropic smoothing kernels to estimate the ETH parameters. We can also use each of these spatial kernels as neurons, and we can use them in artificial neural networks. And by back projection, we can train these artificial neural networks to try to predict the time series occurring on each of these kernels. Another thing which could be useful for physical models is that we can use these fault segments for resolving the fault plane ambiguity, which we often see in the focal mechanisms. And this would give us a way to better model static stresses. So in terms of further improvements to these methods, for example, we can improve the spatial B-value estimation by taking into account joint partitioning both in time and in space, which would allow us to map the temporal variation of B. And we can also use nested Voronoi cells, which we know give us more realistic segmentation of data sets. In terms of the catalog, because we have the waveforms available, because they are made available from the Southern Californian earthquake dataset, we can automatically repick the waveforms, and we can estimate more realistic picking time uncertainties, and we can also get rid of blunders associated with misidentified picks. And we can further improve the catalog like this. Also, we can recalculate the magnitudes based on these location uncertainties, and we can also recalculate the focal mechanisms in a nonlinear probabilistic way. And lastly, for the fault reconstruction, we don't have to limit ourselves to Gaussian kernels. We can use student T kernels with varying T parameters, and we can also use kernels with different shapes, such as banana kernels, for example. So this brings me to the end of this talk, and after the questions, we will have apéro for all of you who want to join.